Can you imagine a place where time stands still, light cannot escape, and all matter is torn to shreds? In this video, we'll journey to one of the universe's most mind-boggling locations, black holes, and reveal the only way to explore their mysterious interiors. Welcome to Enigma Files. On April 10, 2019, humanity captured the very first image of a black hole. This was our first ever photo of a black hole located at the center of the Virgo galaxy M87, about 55 million light years away. What makes this achievement remarkable are two key points. It's the first direct image of a black hole ever captured. The technology used to achieve it was groundbreaking. Normally, photographing a black hole would require a telescope with an aperture the size of Earth. To overcome this, scientists employed an innovative technique by linking 8 telescopes across the globe into a network, effectively creating a virtual Earth-sized telescope. This breakthrough in observational technology allowed them to capture the image. How powerful was this simulated telescope? To put it in perspective, human vision is considered excellent at 1.5. It's said that some shepherds in Africa can have 3.0 vision because they need to see long distances. This telescope's vision, however, reached an astounding 3 million. But black holes are supposed to be invisible, so why is this image so bright? The glowing region around the black hole is caused by its immense gravity, which pulls in gas and dust, making them spin at high speeds. This rotation generates tremendous heat, turning the gas into plasma that emits light, forming the glowing ring. Anything that crosses the boundary of the central dark region, known as the event horizon, is lost forever. That's why the center of the black hole remains pitch black. Why is the glowing ring around the black hole warm-colored? Interestingly, this is likely not its actual color. Scientists added this color to make the image visually appealing. In reality, the ring is probably incredibly bright, emitting white and blue light. It's also worth noting that this image isn't a direct optical photograph. Instead, it's a composite created from limited data collected by 8 telescopes and processed using complex algorithms. To ensure accuracy, researchers divided the data into 4 groups, each independently reconstructing the image. The results were nearly identical, validating the photo. Could all 4 teams have made the same mistake? Technically, that's not impossible. Black holes are actually quite common in the universe, even though they're invisible to the naked eye. We now know that most large galaxies have a supermassive black hole at their center. However, our solar system isn't part of a large galaxy, so its center is occupied by the Sun. But what about the Milky Way? Our galaxy, which spans 100,000 light years, rotates around a supermassive black hole at its center. Scientists discovered this by observing how stars near the center orbit an apparently empty space. Calculations revealed an enormous mass in that region, invisible to telescopes, which could only be a black hole. And black holes aren't limited to galaxy centers. They can exist anywhere. It's estimated that there are over 100 million black holes in the Milky Way alone. Some of these black holes are moving at high speeds. Astronomers fear that if one were to approach our solar system, even without reaching Earth, it could compress the entire solar system into a singularity, wiping out humanity in an instant. Black holes are truly terrifying, devouring everything in their path. And what happens to the matter they consume? Theoretically, it's compressed into a single, infinitely dense point. This photo also holds significant meaning. It proves the correctness of Einstein's general theory of relativity. Over 100 years ago, Einstein introduced the general theory of relativity, which predicts that light bends in areas of extremely strong gravity. So, how strong does gravity need to be to bend light? In fact, even the sun's gravity is sufficient, though the bending is minimal and not easily noticeable. The most prominent example is around a black hole. If we can observe a black hole and see light bending into loops around it, it validates the general theory of relativity under extreme conditions. Modern physics rests on 2 pillars: relativity and quantum mechanics. While quantum mechanics applies to the microscopic world, it becomes less effective in macroscopic contexts. Conversely, relativity dominates the macroscopic world. But how effective is it at extreme scales? To answer this, we need to test it under boundary conditions. Black holes represent such a limit. If relativity holds true even around black holes, it means it is applicable from our scale up to the black hole scale. The next step would be to study the microscopic world and determine whether quantum mechanics is entirely accurate. If proven correct, physics would solidify. But scientists aspire to unify these two theories, relativity and quantum mechanics, into a single framework, encapsulating the entire universe in one formula. However, if such a unification is achieved, it raises a profound and unsettling implication. If the entire universe can be expressed mathematically, it might indicate that the universe itself could be digitized. And if it can be digitized, it could also be simulated, hinting that our reality might be a simulation. What's inside a black hole? Can we traverse it? This question is humanity's next challenge. Now that we've observed black holes from the outside, what lies within? Theoretically, we'll never know unless someone ventures inside. But if you do enter, you won't be able to return. Only you will know. Interestingly, the interior of a black hole might not be as dark as it appears from the outside. Instead, it could be incredibly bright. Light, once pulled in, is trapped and can never escape, endlessly bouncing within. Despite the immense gravity, the interior could potentially be a highly stable environment, perhaps even suitable for habitation. Moreover, due to the extreme gravitational effects, time within a black hole would flow incredibly slowly. If you could survive inside, you might achieve theoretical immortality. Some scientists speculate that advanced civilizations may have mastered the technology to hover within black holes. This would allow them to reside there, effectively achieving eternal life. The Anunnaki, for instance, if they were indeed an advanced civilization, might be hiding inside a black hole. Perhaps Nibiru itself is a black hole where they reside, emerging only to monitor Earth's progress. If it doesn't meet their expectations, they return to the safety of the black hole, avoiding the risks of faster time flow outside, which could lead to rapid aging. We can observe a similar effect closer to home. The sun's gravity is much stronger than Earth's, so time on the sun's surface flows slightly slower than on Earth. The singularities at the heart of black holes. At the center of a black hole lies a singularity. What is it? Some hypothesize it could be a wormhole. Einstein believed the singularity at a black hole's core is ring-shaped, resembling a donut. He theorized that passing through the hole in this donut leads to another universe. While the black hole in our universe absorbs energy and light, it might eject them into this other universe. If it ejects matter and energy, what does that remind you of? That's right, stars. This suggests that a black hole in our universe could be a star in another universe, and vice versa. Our stars might be black holes in a different dimension. Singularities might also be connection points between dimensions. They could link our three-dimensional world to a fourth-dimensional space. Massive black holes, like the one at the center of the Milky Way, might connect us to higher dimensions. If the entire universe is spinning, its center could be connected to the highest dimension of all. One fascinating topic surrounding black holes is the Black Hole War, a legendary scientific debate that unfolded during the development of black hole theories. The central figure in this war, Stephen Hawking. Before diving into the story, let's establish some context. Everything in our world is made of the same fundamental components, atoms. So, what differentiates humans, rocks, cats, and dogs? The simplest answer: information encoded in DNA. While the physical materials forming us are identical, the information arrangement differs. Now, when an object falls into a black hole, its matter undergoes extreme compression and becomes trapped. The question arises, what happens to its information? According to quantum mechanics, information cannot be destroyed. It must exist somewhere. Hawking, however, argued that the information disappears. Other scientists vehemently disagreed, insisting the information had to be preserved. This clash of ideas sparked a war of thought. The resolution? Hawking was wrong. How was this determined? By a vote, hundreds of scientists and astronomers voted, and the majority sided with the view that information is preserved. But where is this information stored? The prevailing hypothesis suggests it's stored on the event horizon, the black hole's boundary. As an object crosses the event horizon, its information is imprinted there, while its matter is compressed, possibly entering another realm. Some scientists even propose that black holes act as information and matter collectors. What's the purpose of this information? To rebuild the universe. At the moment of the Big Bang, this accumulated information and matter could be released, forming a new cosmos. Others speculate that this ties into the idea of a simulated universe. If our world is a giant simulation, then like a video game, it requires efficient memory management. Dead people's thoughts, memories, and junk data need to be recycled. Black holes, in this view, might serve as the universe's garbage disposals, potentially the afterlife's heaven or hell. Black hole observations. The famous black hole photo we see today is of a black hole 55 million light-years away. This means the image shows what the black hole looked like 55 million years ago. We have no idea what it looks like now. Interestingly, if beings near that black hole were observing Earth, they'd see our planet as it was 55 million years ago, when primates first appeared. In other words, they'd see a world full of monkeys. This perspective raises profound questions. For instance, if evolution is accurate, they'd observe Earth's life forms evolving into modern humans. If not, they might see something entirely different. The mystery of the black hole image. Another intriguing detail is how similar the black hole's actual photo is to its earlier simulations. It's almost identical, just a bit blurrier. Could it be that before humans observed black holes, their true nature was undefined, and once we observed them, they formed based on our expectations? Much like quantum mechanics suggests observation influences reality. If so, does our consciousness shape the black hole's interior? Perhaps it mirrors the imagination of its earliest theorists. Einstein envisioned black holes as gateways to another time and space. Could this mean that inside, black holes really are portals to other dimensions? Unfortunately, we currently have no way to venture inside a black hole to verify these theories. A potential solution: quantum entanglement. Quantum entanglement offers a possible way to explore black holes. This phenomenon links two particles, such that their states are instantly correlated, no matter the distance. If we place one entangled particle near a black hole and the other on Earth, any measurement on the Earth-bound particle instantly affects its twin, even if the latter is inside the black hole. This concept hints at a quantum string connecting us to the secrets within black holes. Despite the event horizon blocking all escaping information, quantum entanglement might allow us to glimpse the unknown. Perhaps one day, we'll use this method to uncover what lies at the heart of black holes, the ultimate truth of the universe. If you enjoyed this video, don't forget to like and subscribe.